PFAS are known as the forever molecules. They're polyfluorinated alkyl substances. They are widely used in chemical and commercial products because the carbon-fluorine bond is the strongest bond in nature. And so when you apply a highly fluorinated chemical, you can make a really inert nonstick surface. And this is why PFAS is used to make nonstick cookware, also used in school uniforms, in cosmetics, personal care products, aqueous firefighting foams to fight fires, and in food packaging material, such as the brown paper that your fries or sandwich might come in. They're concerning not only because they're persistent, but they're also known to have toxic effects even at trace levels that they are often found in, such as in drinking water. There is increasing need for more research to better understand the sources and the behavior of PFAS, especially in the atmosphere, and also increasing needs in developing new approaches to remove these chemicals, especially from our drinking water supplies, that don't require a lot of energy or are not very costly. And so to better understand the atmospheric component of PFAS chemistry and transport that can lead to our exposure to these toxic molecules, my group recently developed a technique using chemical ionization mass spectrometry that allows us to directly measure these PFAS molecules in real time in the gas phase and also in the aerosol phase. So my group recently applied what's called a non-targeted analysis approach to understand what happens to PFAS molecules when we treat them by exposing them to strong ultraviolet light to cause them to undergo reduction reactions. And it allows us to really open our lens and understand a much greater fraction of all the different PFAS molecules that are produced, because the end goal is to fully mineralize PFAS and convert it into fluoride ions, which are relatively harmless. But because PFAS molecules are so stable, you often end up with these intermediate PFAS molecules. But by better understanding which of those intermediates form, you can understand how the reaction is proceeding, and then you can optimize the treatment conditions to get a better result. The PFAS problem is a really good example of an environmental and human health problem that, in order to address properly, is really going to require contributions from chemists, from engineers, toxicologists, and also development of better public policies.